Okay. Should I press record?
Yeah, it's
It's happening?
yeah.
Amazing.
It's
Okay, great. Thank you. I'm gonna close this. Hi, thank you all for coming today. Today I'm going to talk about no swap regret algorithms, which we have talked about before in this class, but we're going to talk about a new twist on them today. So let's just start by refreshing ourselves on what this means. So I'm gonna introduce some notation here. So let's say that we have an algorithm, and I'm gonna creatively name it alg. And let's say that at some particular round in a game T, the move distribution that is played by alg is X subscript alg superscript T. Okay, that's what that means. And let's also say that there is some loss function at some time T, which is FT, right? And the actual loss incurred by alg at time T is then FT of X alg T. Okay. And then what is the value, just the payoff of the function alg? It's going to be sum from T equals 1 to capital T of this. Okay, so now what is swap regret gonna give us? So this is just the payoff that you're actually getting, right? And we've talked a lot about, various notions of regret. You can have regret to the best fixed action, but you also might want to have regret to all the times that I played one particular action. Maybe I would have rather swapped to some other action. So let's define a swap function pi, which goes from, and this will be my action space, mappings from actions to actions. Okay, so and I'm just gonna figure out here's the notation we're gonna use here. I'm gonna say that oh, I think that's me hitting something or something. I'm gonna say that I'm gonna apply that swap function to f, and this is gonna be the same as saying f of pi of x. All right, but this will just be useful notation. Does this make sense, everyone? Okay, cool. So now using this, how can I figure out what the payoff is of the best swap function? Okay, so the best swap function, maybe I'll say max over all pi of, and now we're gonna apply the swap function, and then it's over the same actions over swapping them. Okay, so this is what you get over your best swap function. This is what you got before. So this is swap regret. Cool. Does that make sense to everyone? Swap regret. The regret of the best fixed mapping from actions to other actions, keeping the losses fixed. Cool. Okay. So we've talked about this notion before. It's come up sort of directly, indirectly a couple times. This is an example of what would be in the structure that Aaron has introduced to us. Subsequence regret, where the subsequences are dependent on the actions, right? So the subsequences here are all the times I played action 1, all the times I played action 2. So some of the nice closed form expressions that Aaron has developed for solving these sorts of things don't apply here. And we ended up having some min-max, solving for the min-max of a game. So just to give a reminder of what was Aaron's algorithm doing in this sort of setting. Well, what are your losses that you have to care about minimizing? He had, every single possible way you could get lost would be okay, I'm gonna look at all of these subsequences, on which I played this action, and I'll look at what would happen if I played all the other actions. So you end up with n squared different losses, right? And he like does his nice little thing where you try to minimize the max of all those losses, and then you end up with no swap regret. That's great. But there are some things that we might want to improve upon that we'll think about doing today. So what are those things? Here are the two things that we can see from there. So like one thing to keep in mind about that algorithm is it did depend on having like, you want to have n squared weights, right? Because and where n is the number of actions, right? You need n squared different weights. And the other thing is it's a fixed point computation. Okay, and why do we care about this? Well, it makes it kind of hard sometimes to reason about behavior on a round-to-round basis. And I'll give an example of that. So here's something that you might want to be true about, any sort of no regret algorithm, something that seems pretty reasonable, which is say that I said, okay, give me your no swap regret algorithm, and like, here's the sequence of losses, and like, we'll see what happens. Now say I go back in time, and I'm just gonna take one of the days, I'm gonna take one of the actions and make it better that day. Well, it seems reasonable that for the rest of time, in this new scenario where I've changed one of the actions to be better one day, the probability of that action being played should only go up on all the later days. So that's certainly true for multiplicative weights, because multiplicative weights is just looking at the cumulative performance of each action in hindsight. And so you just have this like little epsilon you've added at some time in the past. That's great. But now that we're looking at like some weird fixed point computation, it's no longer clear that that sort of monotonicity property holds. And in fact, while I haven't like explicitly proven it for Ayres' algorithm, I'm pretty sure it's almost exactly the same as Bloom-Monsor, which is another no swap regret algorithm, which is like very similar, also has these two properties. And that one is not monotone in that way. So like these are like nice things that we would want that we can't get here. Now, there might seem to be something kind of fundamentally unavoidable about fixed point computation for this kind of problem, right? Like you're playing an action, and like the action you're playing is affecting what the thing you're trying to optimize is, right? So it feels circular. It feels like it should be a fixed point computation, right? But it turns out it doesn't have to be for no swap regret. So let's try to develop some intuition for why that's the case. Cool. Okay, so first, say that I have a standard multiplicative weights algorithm. I would love someone to help me come up with a sequence of losses that's going to give it swap regret. Anyone have any ideas? Sure. Okay. Okay, so sure. So let's think about let's start here and see what happens. Let's like that this happens for t over 2 rounds, and then this happens for t over 2 rounds. Oh yeah, no, let's actually go straight to 3. To just use a 3 example and say, okay, so say that we have something which is like starts with 1, -1 epsilon for t over 2 rounds. Okay, and then we'll do -1, 1, 0. Okay, for t over 2 rounds. So what's going to happen here? During the first part of play, what's going to happen? Like, say this is reward, not loss. What's going to happen in the first t over 2 rounds of play? Well, I guess like this action is going to be played, right? And then during the second half of play, this action really should be played, right? But in fact, what's going to happen is pretty quickly, this action is going to catch up to being the best. It's going to catch up faster than this action. So during the second half of time, mostly action 3 is going to be played. So what is that going to mean? At the end of time, you're going to be like mostly playing action 1 here, mostly playing action 3 here. You're going to look back all the time you played action 3, and you would have rather played action 2. Okay, cool. So we have swap regret. Now, let me propose an algorithm that fixes this specific problem, okay? I'm going to say, here's my new algorithm. Instead of running multiplicative weights once, I'm going to like choose some value, some number m, and I'm going to run multiplicative weights like m different times and forget about history every single time. So I'm going to have like, boop, 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 boop. This is m in this case. I'll run a couple multiplicative weights. Then at some point, I'll forget everything, I'll start up. So for this particular counterexample, right, as long as we're like choosing m to be, for example, 2, like that fixes our problem, right? Now, once we get here, you're gonna correctly choose action 2 in the second half. Yes. Yes, yeah, good point. It's a small, it's something small. Exactly. Okay. So obviously, like, that's not sufficient because all I've done is gotten rid of that specific problem. But now in this example, like now how are we going to get swap regret? Totally, exactly. So you could just say, okay, I'll do the same cute little sequence and I'll do it in here, and here, and here, and here, and here. Great, exactly. Okay, now I'm going to give you a different algorithm that fixes that problem, but not the first problem, okay? We're just building some intuition here. And that is an algorithm that also plays for the same amount of time. And so like, I'm going to use this circle to mean restarts, okay? This is like the algorithm's restart. My new algorithm doesn't restart. It just only switches its move every m times, all right? So this one keeps its history the whole time. But like after t over m rounds, it like looks at the last t over m rounds, sort of averages it into one loss vector, and then updates here, and then plays that for the next t over m rounds. Okay, so note that while this certainly doesn't address everything, it addresses the specific recursive thing that you just talked about, right? Because now you've done this whole little fancy thing in here, but you're not going to trick anything because it's just going to play the same move during that whole time. Okay. Now you might be like, you're pulling the wool over my eyes. This is ridiculous, right? Because all I've done is said like, this one sort of does well on ones that this one is badly on, and vice versa. But I'm just trying to build some intuition for why, you know, there's sort of like kind of two cases that are happening here. One is that the way that you're tricking multiplicative weights into having swap regret is like sort of this broad, like over the whole course of it thing. And then you can like be forgetful, right? And get rid of that. And the other way is it's like sort of like in a cyclical way. And then you can sort of be lazy in evaluating what your next move is, and you can get rid of that. Is there a way that we can compose these two ideas in order to get a no swap regret algorithm that like just sort of combines multiplicative weights in some weird way, doesn't do any fixed point computation, and doesn't necessarily run in a way that is dependent on the number of actions? That's what we're looking for. Okay, so does the question we're going for make sense? Okay. So what's the algorithm? It's weird. It's fun. It's good we have a board because it's kind of useful to draw. And what should I erase? I guess I'll just erase this if I can find an eraser. Oh, thank you. Oh, there's so many. Okay. Okay. So like we're sort of, oh wow, this is a really bad eraser. Oh. Okay. Well, okay, it's fine. Okay. So the algorithm needs two numbers, m and d. Okay. And we're setting them so that t equals m to the t. Okay. For the purposes of this lecture, I'm just going to be assuming it's exactly equal. Like actually with not that much more work, like it's okay if it's like sort of like approximately equal, but like let's just deal with the t's for which this works. Great. What's d? Oh, it's a surprise. I mean, I haven't told you yet. Yeah, like these are just, we're gonna pick these numbers later so that they get us the guarantees we want. But right now I'm just telling you that when you raise m to the d, you get t. Okay, so this algorithm is kind of weird, but it's cool. So it basically, you can think of it like a tree. By the way, this is a recent paper. There were two recent papers that basically came up with almost the exact same algorithm. And one of them was, I feel like I shouldn't say any authors because I can't remember all of them, but I'll say it at the end. Okay, so we're gonna have d layers of this tree. It's a d layer tree, and the fan out is m. Okay, and every node is an algorithm. Fun, right? At every layer, what you have is, so like, let's just start with the top layer. And I guess I'll call this d equals 0. Top layer is going to be a no regret algorithm that we're just promising has no external regret. And we're going to run it, I guess for the purpose of the example, I'm just going to like say that m equals 2 because it's easiest to draw, but like it doesn't have to be 2. It's probably going to be bigger than 2. It's going to be a just multiplicative weights. But it's only going to update what it's playing 2 different times. Okay, so kind of silly, but like that's what it's doing. Okay, certainly that's not all we need because that can't just be no swap regret because of what I already pointed out. So now let's go to the next level of the tree. What is this going to be? Well, we're going to think about each of these algorithms as being like some sigma, and they're each going to have 2 children because the fan out is m. And between these, I'm going to use this to mean like total algorithm restart. I'm going to use this line to mean this is just where we compute the next move. Okay? Okay. So at this level, we now have an algorithm for that basically it's gonna, for the first t over m time steps, it's gonna run, and it's going to compute the new move m times. And then for the next t over m time steps, a new algorithm run, it computes the next move m different times. And now we're gonna just make the tree even smaller. So we're gonna keep doing this. Okay, and like it just keeps going. Okay, so like I haven't really given the algorithm yet, right? I'm just like drawing this weird combination of algorithms. What's the actual algorithm? The algorithm is that at every round, you're gonna like maintain at least the necessary part of the structure you need. You can do it in a more efficient way than literally remembering and building all of this the whole time. And then you're just gonna take the average at any particular time t of what each of these levels tells you to do, right? And at level, for example, level 2 is telling you like, oh, cool, I'm now looking in this particular algorithm, and I am looking at what move it computed I should do, like at this one of the steps. Does this make sense to people? Because this is like important that we understand this part. Yeah. So I'm using the dot to mean you restart your weights. So like you're starting a whole new algorithm, you've forgotten history. The line just means during the whole, any box without like that has no line in that, during this whole time, this algorithm is playing the same move. So it is only recomputing what move it should play right here. So it's going to pretend basically that instead of playing a T round game, it's playing a T over M round game. And so, an M round game. So at time t over m, it looks at all the losses that it ignored. It's going to average them up, and it's going to treat that as a one-step loss in the game it's playing. We'll explore this more, but like that's the idea of what's happening. Make sense? Yes. Yes. Yeah. That's perfectly fine. Yeah. Yeah. Totally. Yeah, I think it's sometimes useful in the proof to like think about children of and think about it as a tree, but certainly that's entirely correct. Like you could just think like what's happening this level, it is recomputing its move here, it's forgetting everything. Right. Okay. And just as a reminder, like m equals 2, if m equals 3, then we would have 2 blinds here and we would also have 2 dots here, right? Okay, so like let's already notice one interesting thing, which is like every single, if you look at a particular algorithm, right, and you look at its children, then during the entire time that it's playing a fixed move, like that's when like one of the children is out. So like m is being used 2 ways here, right, as the fan out and also as the like number of times you compute something. Just an interesting observation. Yeah. So okay, so m is sort of used 2 ways here. For any particular like algorithm, when I'm using algorithm to mean like you are keeping some memory, right? You might be lazily computing your move, but like you haven't gotten to this white dot, like you're not erasing history. During this time, that algorithm is going to recompute its next move m different times. It also has m children, right? And those children are each going to run for the exact amount of time between when it recomputes moves. That's just sort of the observation. So, okay. So why is this going to get us what we want? So let me give some intuition. Yes. There's no what? Well, they're all experiencing the same history. Yes, you run them in parallel and then you just take the average to see what you should do. Yeah. They're correlated because they're both taking the same. Yeah, but their randomness is not correlated. Yeah. Sure. Okay. Let's give some intuition. I've sort of gone back and forth on whether this intuition is itself a proof or not, but like let's figure out because I think it's pretty good intuition and the proof is more complicated. Let's see how this goes. So let's say that I wanted to just look at like one way I could compute the swap regret of this whole algorithm I've just come up with is sort of looking at the contribution to the swap regret of each of the levels separately, right? I could say like, you know, okay, like the swap regret contribution. Okay. Yeah, I'm just gonna say that for now. And now I'm gonna say, okay, well, let me define 2 different things. Let me define for a particular level Ri for level I, and Ri is the average reward. Let's name this algorithm. Who has a good name for it? Call it Noopy. Noopy. What? Oh, great point of Noopy I. Yeah. Okay, so that's that. And then we have another thing we're gonna call SI. And this is if you looked at all of the different like algorithms at that level, right? And again, when I say algorithms, I mean things, points where you totally forget history. then this is going to be, and I looked at the best fix action against that algorithm. This is going to be the average of best fix actions against algs at level I. Okay, so like here it would be, for example, at this level, it would be you have like RI is the actual thing that happens, and then SI would be like, okay, let me figure out what the best fix action is here, you know, and the payoff of that, payoff of that, payoff of this, payoff of this, and then I'll average those together. So it's different from just the best fix action against this entire level, right? It's granularized by the number of algorithms. Cool? Yes, they're both numbers. They're payoffs. Well, it's not, I mean, it's sort of an imaginary number, right? Like we're saying RI is the actual average reward you get at that level. SI is if you looked at the best fix action against all of the particular algorithms at that level, and took the average of that payoff over the whole thing, that's what RI is. I mean, sorry, what SI is. Sure. So let's just like look at this particular level. What is RI? It's just, let me just look at the particular, all the algorithms running at this level and what they did during the whole execution. And let me look at like what the reward would be of just like running NuPI, right? That's what RI is. Now, let me look at if instead of doing that, I was able to play the best fix action during this particular, during every single one of these algorithms, right? It was playing exactly the best fix action, right? Yep. Yeah. Do you have a question? Okay, cool. So now let's consider for any particular level, right? What is the best that you could do with a swap function? All right. So this is where like laziness is important, right? So let's just like look here, right? Note that like during this time period, only one action takes place, right? Same action. Same for this, same for this, same for this. Cool. So what's the best swap function that you could have? Well, it would be best responding on average over this time period, right? Same here, same here, same here. Okay. So what is the payoff that you would get if you best responded over this time period, this time period, this time period, this time period? It's exactly SI plus 1. It's exactly that value I just said, but for the level below it. So we can go through this as many times as we want to get the intuition, but I'm just going to write the statement. I haven't used it yet. I will, but that's not what I'm doing right now. I'm just using laziness. What? Yeah. So I'm just saying that like, what is the, yeah. Val of best swap at level I equals SI plus 1. Okay. So now if I want to figure out at that level what the actual contribution to the swap regret is, then I would just take SI plus 1 minus RI. Okay. Yes. Okay, so let's think about swap regret. So do we agree that the best swap function at this level is just playing the best fix action right here, and then also right here, and right here? Okay, so if down here you play the best fixed action here, 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 and here, then that would be playing the best fixed response against all the algorithms. So like, I think maybe your intuition, like, it's just like, I think you're getting at the right thing, which is basically like every single time during the entire time that the parent is playing a fixed action, like during that entire time, no longer and no shorter, is when one of its children is active. So if you could make sure that you were doing as well as your child could possibly do, like if it was just playing a fixed action, then you'd be done. Like if we could ensure that this child was sort of playing roughly no regret, getting ahead of myself a bit, then that's pretty good for our swap regret. Okay, but like right now, all we have is what's the swap regret? And again, this is like, I'm just doing the intuition right now. This isn't full proof. So like we're being a little loosey-goosey, but you know, like we're going to sum up for all the levels. Do that. Si plus 1 minus Ri. Cool. So you might notice something kind of nice about this, which is we can turn this into S of E minus 1 minus R0 plus okay, now's where we use the no regret property, which is basically like, okay, so what's this here? Well, here we're looking at the actual thing that you got at that level. And here we're looking at what you would get if all the different algorithms at that level played as the same as the best fixed action, right? Okay, so if those algorithms are no regret, then we get what we need. Now, you might think, this is kind of suspicious because you're sort of implicitly assuming that these are no regret algorithms, but they're not really, right? They're sort of like no regret, but they're like updating lazily, right? But the key is if we choose M and D appropriately, then this is going to give us what we need. And by the way, just to finish out this analysis, what does this leave us with? Well, this is going to end up being like something like epsilon, where epsilon is the regret of the internal regret algorithm, right? And we can get rid of this because it's a negative. And then this is just the best that you could do at like the final level, right? Oh, there's something important here, which is we're averaging over all the levels. And so what's happening over here? Well, we have the sort of at the final level, at the lowest level, it is the average of the best fixed actions against the algorithm. And so because the chaos we're going to assume are upper bounded by 1, then this whole thing is less than or equal to T over D plus oh, and I guess I shouldn't call this epsilon. I should, and again, we're going to get more into this, but it's something like regret of M. So that's the vibe, is we sort of end up with these two different terms. And the intuition, right, is like, you know, if we make this tree have like fan out that is too small, then or rather, I guess maybe like if it has not enough levels, then we're going to lose too much with this approximation of like not really worrying what happens on the lowest level, right? But if we have too many levels and not enough fan out, then like the regret of these like lazily updating, you know, regret algorithms is not going to be comparable to like what we really need. And so then we won't get what we need either. So we need to set them appropriately. But you all see sort of see the trade-off of what's happening here. Cool. Okay. Great. So a little bit more about the significance of this result before we get into the proof. We're not going to be using anything explicitly about the size of the action space. The thing that Aaron showed in class and also the classic Bloom-Mansour swap regret algorithm are also reductions from external regret algorithms to no swap regret. But in that reduction, they have to then use again n, the number of actions in part of their construction. That doesn't happen here. We just need the fact that these no external regret algorithms exist. And then we can get that a no swap regret algorithm exists. So this is going to let us do some nice things in the context of a finite action game that, like the kinds that we have seen in class. It lets us have a much better dependence on n. And in the case of games where there exists no external regret algorithms, even though the action space is infinite, which do exist, I don't know much about them, something about Littlestone dimension. In those cases, it previously was not at all apparent that you could do anything here, and now we can see that we can. So, great. Yes. Will they depend on what? So this specific instruction is pretty specific to subsequence because the reason that it works, right, is because of this lazy evaluation. We're basically forcing the subsequences, which are depending on our actions, to now be dependent on you sort of see what I mean? Right. That being said, if another part of your question is, could you take this, power it up with other subsequence regret things? The answer is probably yes. I haven't thought about it a lot, but like if you use this as a black box, plug it into Aaron's other algorithms, I feel like you could get some good stuff. I don't know. We can talk about it. Okay. Cool. Are you all ready for this proof? Heck yeah. There's got to be a better way to do this. Yeah. Maybe the next one will work better. No. Okay, it's fine. It's just, I'm just gonna have to write powerfully so that you can see it over this cloud I've created. Okay. So we're gonna start by just writing an expression for the payoff that this algorithm gets us. Okay, so let's start simple. So remember, because what we're doing at every round is we're taking an average over the distributions given at each level, we could just take an average over what the utility of each level would actually give us if it was run as its own algorithm. So that leaves us with, and then I'm just gonna like, for now, just write this. Basically, what am I saying here? I'm saying like, this is like let me do this correctly. There we go. That's like the thing happening at that level, right? Okay, so now we need to expand this part. Can you all read what I'm writing on the board? Yes. Okay. Okay. So now I'm going to break down this, and I'm going to introduce some notation. So I'm going to write this, and I'm going to tell you what it means. Second sum. Oh, well, I mean, it's a sigma 0 to h, but you don't know what it means yet, and that's reasonable. Definitely have too many sums. What happened here? Oh yeah, I skipped a step. Sorry. Yeah. And I think in just formalizing all the rest of the argument I said too. Okay. Okay. Let's break down what happened here. Okay, so this part's the same. And now I'm just looking at a particular level, what is the utility? Okay, so this is sigma subscript 0 to h. What I'm using that to mean is a particular sequence. I'm using this to mean we can think about every single algorithm in this tree as being defined by a particular traversal down the tree. And I'm using sigma 0 to h to be some particular node / algorithm, right? So I'm looking at like every level, then I'm looking at every algorithm at that level. And then I'm looking at, for every one of those algorithms, this is like, I'm sort of writing this, the notation they use in the paper, so that those who want to read the paper will find it easier. So don't blame me, but they have this tau of sigma 0 to h and they have like a tau underbar to a tau overbar. And this is basically all of the rounds in which this algorithm is active, okay? So we're looking at like every level, every algorithm at that level, all the moves, all the turns on which that particular algorithm is active. And then we're looking at, and now note I have s not t because I'm just using s to count the turns here. I'm saying, okay, what's the loss vector or the loss function at that time? And then what is the algorithm defined by sigma 0 to h playing at this round at time s? Does this make sense? Okay. Okay, so let's expand this further. Instead of considering the nodes of that round, I want to consider their children. Now, in order for me to square the indexing and make it really work, I think you have to hallucinate there's an extra level of this tree that's not actually used in the computation. So like just hallucinate that for me. Okay, so I'm gonna like further expand this. Oh no. Okay, so this part stays the same. Sigma. Okay, looking at all of the nodes at that level. But then we're going to look at all of its children. So that's why it like would be weird to do this if like we're looking at the leaves. Okay, so we're going to look at all of its children. And so those are like defined by sigma of h plus 1. Going from 0 to, I guess, like m minus 1. They call this m prime because they are also concerned with when t doesn't exactly equal d, but I don't care. This little loopy thing, that's fun. Okay, cool. So now I can no longer count over the times that I'm active. I actually have to count over all the times that my child is active. H plus 1. Okay, and now I can add this part in again. But note that like this is not h plus 1, this is still h, because I'm still thinking about all the times that I'm evaluating this particular algorithm. I'm just saying like, instead of counting all the times that I'm active, I'm going to look at all my children, count the times they're active, and then think about what I'm doing. This is just like a change notation. Like it's the same thing. Okay. So that's it. Like I'm just like, let's start with like, this is a way to write the total utility. Are we all okay with this? Okay. Now let's consider the swap function payoff. So we can consider maybe this should be soup or something, even if an action case, but let's just do this for now. Okay, so what am I gonna do? I'm just gonna take this, right? And I'm just gonna like plug in the swap function. So this part's all the same. We got then we got sigma 1 to h, and then we got sigma h plus 1, and then we got this underbar tau h plus 1 to overbar tau, and then we have f of s with this pi of x to the s sigma 0 h. Okay, so all I've done is added in this, and I'm saying like pick the best pi for this. Okay, cool. So I'm gonna try to upper bound this, right? So like one thing I could do that would only make this larger is I can move this max in, right? I can move it all the way in to here. All right, so this is only gonna like help me because I can like take more granular maxes. This is gonna upper bound stuff for me. Great. So, and then once I do that, we can collapse these things, right? We can just go back to saying like, well, what is this? I'm just like summing up over like all things going up to h and then all things going up to h plus 1. So let's just do those things together and say this is equal to or less than equal to. I'm just going to be lazy about the notation here, but I think you all know what's going on. Okay. Okay, cool. So note that by definition of the algorithm, during the entire time, well, I guess maybe it is actually useful for me to be very clear about what this is. So what is this time period? It's the time that its child, a particular child, is active. Right? Like we're looking at something at level H. And here we're looking at a particular one of its children, and we're looking at the whole time it's active. Okay, so what do we know about the behavior of this X? Anyone want to tell me what we know? Exactly. So that's awesome, because that means that we can just rewrite this as well, I'm just saying like, sure, we could do some fancy swap function, but actually there's just one move. So the only options we're looking at are like all single fixed moves over the whole thing. Great. So this is our expression for the swap function payoff. That's our expression for the total utility. So the next thing we're going to do is we're going to subtract them from each other. What should I erase? Is it, I'm not sure if it shows up on the camera. doesn't matter that much, but okay, yeah, we'll just fit this. Okay, cool. Yeah. Yeah, that's right. Okay, so I'm trying to figure out the most, I guess I have 35 minutes left, right? So I don't want to try to rush things, but I want to explain this. Okay. Okay. I mean, the next part of it is going to be kind of similar to like the intuition that we did here, right? We're gonna like we're gonna make a sum kind of similar to that. So we're gonna take this object, we're gonna take that object, and we're gonna subtract them from each other, and that's gonna turn into okay. So this is the part of the sum that we can combine together. Because like just to be clear what's happening, they're both summing over from h equals 0 to d minus 1. But then one of these we're looking at like a level h, the other one we're looking at level h plus 1. So we're gonna like realign those. Yes. You're talking about this line? Yeah. So it's exactly because by the way we've defined the algorithm, the entire time that a child is active of the parent, that parent is always playing the same action. So yeah. Okay. So this is one part of this subtraction, which is just the part where we have like aligned the levels to each other. And then the other part is just 1 over d. We're just looking at like the dth level. And this dth level is like, I guess, a little hallucinated, but it's fine. And you'll see that it's fine. This is basically like just looking at like the contribution at the dth level of all of the different moves and the best fixed response. Okay. And then there's also a subtraction term, which is from the thing you're subtracting over here when this one's lower. Sorry, I'm sort of skimming through this, but I hope you get the intuition because we're kind of trying to do what we're doing there. We don't care about that subtraction term. So we can just like, we can like up or bound this by this. Okay, so now what's going on here? Going back to our intuition, right? This is like the contribution of what's happening at the last level. Like this is, you know, we have this whole like process where like we're going down levels and saying like, oh, okay, like maybe we have some swap regret of this, but like, you know, at the lower level, we did that well, and then we recurse down and down. But once we get to the final level, we have to deal with this. But using the same logic as before, like, okay, cool. Well, this is at most 1, right? And so this whole thing, this part of it, this is less than equal to 1 over d times like all the different I guess not even writing that, like, okay, so like what's happening here, we have all the different times that all the different algorithms that are active at level D, right? And then we have for all those algorithms the amount of time they're played. Okay, so even if we've hallucinated this extra level, like when you add those up, we're gonna get T, right? Because all these levels are just going for T rounds. So if we're first saying that this is just like, we can turn this into a 1, and then we're going to combine these sums, we just end up with T over D. Okay, so that's this part. What about this part? This part is the part that's kind of like this part. Now let's think about exactly what this expression is. All right. This is this is X star. This is the best fixed action for some particular algorithm at level H. And this is, what's this how doing here? Right. Let me just figure out the written down exactly what I want to write down. Right. So one thing we can do is we can like rewrite this part. Like what's this? This is just saying all the different things at level H plus 1. And then all the times they're active, right? This is the same thing as looking at the entire time that their parent is active. So I'm just gonna watch, I'm just gonna like look at this part of the expression, right? And rewrite this as so exactly as you said. This is just the best fixed action across the whole thing minus what the algorithm actually did. Okay, so now is what we have to argue something about the regret of this particular algorithm, right? Now, if the algorithm were actually just multiplying the weights, like we'd be done. It's not, but here's a cool fact, right? Like, say that I had some algorithm and it, you know, if I ran for T rounds, it would get regret like total regret f of T, right? Okay. So now let's say that I have a new algorithm that like only updates, you know, every T over M rounds. Okay. So now we can just pretend we're playing a game that's M rounds, right? in that game we're playing M rounds, the best fixed action is the same, right? So the thing we're comparing to is the same. It's just that our performance might be different. So now in this other world, what are we getting? Well, we are getting a regret of f of m. Okay. So why is that good? Well, it depends what we're setting m as, but we can just turn this part into regret of whatever our like alg is over m. Okay. And now just like combining all these facts together, like what is the actual upper bound that we get? Well, we have this 1 over d h equals 1 to d minus 1 of, and then we have this, everything on level h, and then we have the regret sorry, let me just we still need to keep this sum. This sum still needs to go here. Yeah. Yeah. Yes, exactly. Well, right. The times that like the sequences could come later, like this is exactly around. Exactly. But yeah, you're right. Like I think before I might have also described this as a total. Like it is important to say like this is an average. Exactly. Like, right. Like if m is 2, then your average regret could be like 1 over root 2, which is a constant. And then, yeah, exactly. Right. If m is totally independent of t, then like we'll run into some problems. Okay. So now what am I doing? I'm just like plopping this back in here, right? So we have to put back in the under tau to the over tau. And then finally, reg alg m. And then we also have this t over d. Okay. Sorry, this is getting kind of messy, but like we're almost there. Let's look at what's happening here. So obviously we can upper bound this by just getting rid of this part because that's just counting up to like almost d divided by d. So what we're left with is at the particular level h, all the different algorithms. And then again, I guess it's important for me to keep exactly what this subscript is. This is h. This sum? Oh, this is just like, this tau is just always looking at, for some particular algorithm, like all the turns that it is active. So here we have all of the algorithms at level h, and then for each of them, all the turns it's active. This is just t, right? Because there's t turns at level h. So we can get rid of all of that and replace it with a t, right? So this equals reg alg m times t plus t over d. And remember, we never normalized at the beginning of this. This was like if we look at our original expressions, they're cumulative regret and cumulative swap regret. So if we divide by t, we get the average, which is going to be 1 over d plus this average regret according to m. Okay, so that's the high level result, but of course we have to show that we can set them in such a way that this gets us something useful. All right, I'm going to come back over here. Okay, so let's talk about a setting that we like, the expert setting. And let's consider a case where first let's assume that T is greater than or equal to log n over epsilon squared to the power of 1 over epsilon. We're going to try to get, what we're trying to do right now is say, like, we want to get epsilon average swap regret, right? For some fixed epsilon, which could be kind of small. You know, what do we need M and D to be in order to get there? Which is a little bit different from the way that we normally think about this. Yeah, what's up? Right. Yeah, I mean, I agree with Ira's intuition. Like, it would be great if it were true, but if that were true, we should just use the final level, right? But yeah, it's right. So somehow they're all fixing each other. Yeah. Yeah. It's kind of weird too, though, right? Because I totally get what you're saying, but also, like, you shouldn't really be able to significantly improve. You shouldn't be able to, like, improve in general on a no-swap algorithm over all instances, right? Okay, but you're not suggesting improving like by a constant. You're saying it might be possible to improve by sublinear, but then you might have swap regret increase by a constant. Yeah, I think that's entirely possible. Yes. In some places, it's possible. Yeah, it's an interesting question, but yeah, it's swap regret is a weird property because you can do better and have more swap regret, right? Like, I could play one fixed action during a whole game, and maybe I it wasn't a very good action, but like no fixed action was that good. But then I could play like some really complicated, but like pretty good complicated sequence actions. But now I'm leaving myself up to like, a much more granulated swap function that could be much better. So it's weird. Okay, but let's just quickly show that at least in the expert setting, there's something we can do. So I'm making this assumption. I'm going to set M to be equal to log N over epsilon squared. Okay, and I'm going to set D to be greater than or equal to 1 over epsilon. It can be anything larger than this as long up until we get to T equals MD. By this exact assumption, it is possible to set it to be at least 1 over epsilon. Okay, so now I can just plug in these values, and what do I get? Well, let's say that we're using, oh yeah, and I guess I should say, like, what's the algorithm I'm using? So let's say I'm using multiplicative weights, right? So if I'm using multiplicative weights, then what's reg of MW of M, well, it should be equal to root log N over root M. This is just the definition of multiplicative weights where I've replaced M with T, or T with M. Okay, and then I also, of course, have 1 over D. Okay, so I'm gonna like put in the values I want. Great, so this becomes, this part becomes less than equal to epsilon, and then this part becomes exactly epsilon. Like, you know, you just plug that in there. It's the optimal choice for N. So, right, okay. So what is happening here? This is great. We are able to get for any arbitrary epsilon, a M and D, that's what we want. But notice we had to set T pretty big, right? So we had to set T, so note that like small epsilon means big exponent, right? So like it's exponential in like the smallness of the swap regret we want. But it's great in terms of N. We are able to, instead of doing this thing like in Aaron's algorithm where we have to like maintain N squared different weights, and also just the runtime of that, and also Blue Monster end up being linear in N, we end up having a runtime that could be logarithmic in N, and which also at each time step, right, like we don't really need to maintain all of these at once, right? So at every single step, we're really just maintaining D different things. And this D, well, it could be very big, right? It doesn't have to depend on N. Okay, so that's interesting and good, but also has a terrible dependence on T, right? Like, let's now like pretend that N is a constant, right? Let's say like we didn't care about N and we just cared about T, right? And so like this is basically our bound. So like now, what do we want to do to equalize these? Well, you know, I mean, like, I guess like we basically just want that M is that to be equal to D squared, right? And we also have that M to the D equals T, right? Which means that D to the 2D equals T, right? And like, what am I saying here? I'm basically saying that like, if you want to get a error, average error of 1 over D, you have to run for D to the 2D steps. Okay, well, that's really bad, right? So if you care about T, then that's not very good. But it's still pretty interesting, right? Because even if we didn't care about N that much, just care about T, we were just able to come up with a algorithm that does, you know, it does decrease pretty slowly, but it does decrease the average swap regret. And it doesn't use fixed point at all, right? It kind of relies on the fact that as long as you're playing the same move like a reasonable amount of the time, or like for a long enough chunk of the time at once, then swap regret becomes kind of a simpler object to analyze. And it's possible to still get bounded regret by doing that sort of thing. I guess I'll very briefly, well, I guess first any questions about this? Cool. So then I guess the last thing I'll do is I'll briefly talk about infinite size action spaces. So for a pretty similar analysis to what we're doing here, right? We can sort of forget about N entirely and say, you know, if you had some algorithm, some external regret algorithm for some setting, and it got average regret of any like m to the negative alpha, right? Which just to like for our understanding, right? Like in the expert setting, like multiplicative weights can get this with alpha being 1/2. But if you have this for like any setting, then what can you do? If you want to get any arbitrarily small epsilon no swap regret algorithm, well, you can always just basically set d equal 1/epsilon, right? And then we can think about what exactly, so our average regret is equal to, and that of course means that because m, the d equals t, we know that m equals t to the epsilon. Okay, so what am I doing here? All I'm doing is trying to tell you that if we do this, our swap regret ends up being, again, we have 1/d plus m to the negative alpha, right? And then this is now equal to epsilon plus t the negative epsilon alpha. And I want to find this so that it's less than equal to, I guess I'll say 2 epsilon because I have this epsilon here and my constants are fine, right? So I want to figure out like, okay, I'm going to set d to be 1/epsilon. I would like my total swap regret to be less than epsilon. Like, what do I need t to be, right? And we can just solve this and find that like, if t is greater than or equal to 1/epsilon to the 1/epsilon alpha, then we're good. And so as long as alpha is greater than 0, right? This is like well-defined. They're like, is such a t. Okay, so this does not mean that it's efficient, but what's really nice about this is it's a cool existential result. Did we talk in this class about correlated equilibria? Correlated equilibria? Yeah. So one nice fact that's true is that if one way to compute a correlated equilibria in a game is to simulate all the players playing a no swap regret algorithm. So if you have the existence of a no swap regret algorithm in a game, then you have a tool to compute a correlated equilibria. So before this result, there were some games with infinite active spaces where it was not obvious how to compute or if there was a correlated equilibria. But now we have the fact that for all action settings that have external regret learners, you have an epsilon approximate correlated equilibria for any epsilon. Yeah. Yeah. Wait. Sorry. In general, you're going to get a sampling oracle for what? Sure. Mm-hmm. I think it'll also be good enough for the purpose of, I think that it's the case that if you just actually look at the samples and you run T large enough, that like this is also an approximate correlated equilibrium. You don't need to see the distribution every round. Mm-hmm. 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 Mhm.
And to make the log of the quality as the number as the reducing power of so you want your samples to fall into the satisfaction of the quality of the
Mhm.
and I think the concern is that for finding the number the median bound number of people log and then add an additional log and transfer to your sample. But this is actually but maybe but it's not really.
So your issue is with, it's with the sampling?
Yeah,
Yeah, I mean, I see why that would be something you'd be concerned about. I don't really know the answer. I know that they do claim this result in their paper, so it's probably true, but like, yeah, infinities are weird. So I wouldn't, I don't know anything about infinities. They're impossible. Yeah, okay. Any other questions? Cool. Okay. I'll give you all back the time then. I gotta figure out whether this actually recorded. If I just press stop video, do we think it'll? Okay. Oh yeah, you did so good. Thanks for being such a good active listener. Oh, thanks. This is being recorded, isn't it? Oh no.
Thanks for the lecture.
Thank you for coming. Bye, friend.
Hey, look.
Thanks. Thanks, friend.